Jai Hind students, myself Parveen Kumar, Assistant Professor in AKGEC, Ghaziabad, and today we are going to discuss about the subject that is Basic Signals and Systems. The subject code for AKTU for this subject is KW303, and today we are going to start Laplace Transform, and this is basically introductory lecture about Laplace Transform, what is Laplace Transform, why we use it, what are the applications, and what are the basic steps involved in Laplace Transform. So we will discuss those. So these are the contents. Firstly, the basic introduction about the Laplace Transform, then applications, then some basic example we will see, then as I said already in the starting of the lecture that this is basically the introductory lecture of Laplace Transform. So we here basically study about the necessary requirement for the computation of Laplace Transform, and basically we are cover in this part these three things: integration by part formula, Euler equations, and partial fraction expansions. So you can say these are just for your reference purpose. These are basically the parts of mathematics. So let us start the discussion. So you can say if we have any signal xt which is real or maybe complex value, then suppose that function is exists for t greater than 0, where s is a real or complex parameter, then Laplace transform is given by this formula L xt, that is represented by capital Xs, and this is integration 0 minus to infinite xt e raised to power minus st dt. As I already stated here, s is a complex variable, that is s is equal to sigma plus j omega. Okay, s is sigma plus j omega. This is the real part and this one is imaginary part. Okay, and just keep in mind here the transform is written in uppercase only, and 0 minus is included to involve the signal impulse at t is equal to 0. Okay, so this is a complex variable already stated, and unit of s complex variable is second inverse. Okay. So this is basically one-sided or unilateral Laplace transform formula, and we are basically discussing about in this subject electrical signals. So they are basically starting from 0 and goes up to infinite. Okay, so we only use this one-sided Laplace transform formula. Of course, there is bilateral two-side version also. Xs is equal to, here only limit are changed from minus infinite to plus infinite, the rest will remain same, xt e raised to power minus st dt. Okay, so here we will work only with one-sided version already stated, and why we do it? Because we are dealing with electrical signal and it is easier to obtain the transient response in this case, and these are basically consistent with common practice, and we here ignore xt for t less than 0. So now the question arises, if the signal exists from minus infinite to plus infinite, then what to do? Case is very simple, multiply the signal with ut, that is unit step signal, and your problem will be solved out automatically. So we will see it in the coming video lectures also. So let us discuss it further. So basically we use the following Laplace transform pair. xt ut Laplace transform pair is capital Xs, this one, where Xs is, you can write down like this, Xs is equal to L xt. Okay, and xt ut, this is inverse Laplace transform. We will discuss in coming video lecture. So today our focus is basically about Laplace transform only. So this is basically inverse Laplace transform formula, xt ut L inverse Xs. Okay, so this is the basic introduction. Now let us discuss about why we need Laplace transform. What are the necessity for Laplace transform? So applications. So basically you can see here Laplace transform is basically used for solving out the differential as well as integral equations. Okay, detail about these we will discuss in the coming video lectures, but just here to give about the some basically knowledge about this concept. Just assume, suppose you have any function or input xt, continuous input or excitation, and that is applied to a system having the impulse response ht. Okay, then suppose the response or output is yt. So suppose this system is LTI, linear time invariant system. System is LTI system. So what will be the output here? Yt is equal to, yt will be equal to xt linearly convolute with ht, and if you solve it out, that will comes out to be integration from minus infinite to plus infinite, you can say x tau h t minus tau d tau. Okay, so here we require basically integration in this case, but if you do Laplace transform, then Laplace transform for xt will be xt signal Laplace transform is represented by capital Xs. Similarly, ht Laplace transform is capital Hs. Okay, and similarly you can find out yt. Yt is equal to, yt will be equal to Laplace transform is capital Ys. If you find out the Laplace transform for these three variables, then our this types of equation will basically convert into simply this equation. Ys is equal to xs into hs. Okay, so this is simple equation. Okay, so you can see here this is simple multiplication. Then we find out the inverse Laplace transform to get yt. So here we apply inverse Laplace transform, which we will discuss in coming video lecture. So basically idea about telling these things is that the applications of Laplace transform is basically in the solving of differential equation and integral equation, and basically if we apply Laplace transform in any system which is linear, then the complexity is reduced by manifold. You can say simply integration is converted into simply multiplication. Okay, so that's why it can be seen that it is very much necessary to study about the Laplace transform, especially to understand the basics of signals and systems. So let us discuss some common examples. So let us see. So let us discuss one example. Suppose your function ft is, suppose you have function ft. Ft is equal to, just ignore this, ft is equal to ut, unit step function, and question is find out fs, that is Laplace transform. Okay, so as you know, if you solve it out, then you can see that fs is equal to integration 0 to infinite or 0 minus to infinite, you can say ft ut. So this is not ut, so just wait a minute. Fs is equal to integration 0 to infinite, 0 minus to infinite, you can say ft e raised to power minus st dt. Okay. So here ft is, in our case, that will be ut. Okay. So that will become ut e raised to power minus st dt. So if you solve it out, then this will become 1. So this is 1, as we know, from 0 to infinite limit. So if you solve it out, that will comes out to be fs is equal to integration 0 to infinite e raised to power minus st dt. So that will be comes out to be, if you solve it out this integration, so that comes out to be e raised to power minus st upon minus s and t from 0 to infinite. So that if you solve it out, that comes out to be 1 by s, 1 upon s. So that comes out to be 1 upon s. So you can say ut Laplace transform is 1 upon s. Okay. So this is one example. So let us discuss the another example. So now suppose ft is equal to kut. Okay, ft is equal to kut. Then in this case, we have basically the fs is where k is a constant, so directly you can find out that will comes out to be k upon s, Laplace transform. Okay. So let us discuss another example. Suppose question is ft is equal to t, or you can say ft is equal to rt. That is ramp function. That is basic signal or function, continuous. So find out, question is find out the fs for this. Okay. So how to find out? So simply, if you solve it out, then you will get fs is equal to integration 0 to infinite. First function is t e raised to power minus st dt. So if you solve it with the help of integration by parts formula, I will discuss integration by parts formula in the coming slides. So if you solve it out, that comes out to be fs is equal to, that comes out to be 1 upon s square. Okay, that comes out to be 1 upon s square. So I will discuss this formula. This is integration by, here we apply, in this numerical we apply integration by parts formula. In short, I write down here IPF, integration by parts, IBF, integration by by parts. Okay, so integration by parts. So I will discuss integration by parts, integration by parts formula. Okay. So let us discuss this numerical first, then I will discuss integration by parts formula. So let us discuss this numerical. So here fs is equal to, for our case, fs comes out to be integration 0 to infinite t e raised to power minus st dt. Okay. So this is first function, this is second function. Okay. So first function as it is, integration of second, this function. So that will comes out to be e raised to power minus st upon minus s. Okay, and here limit are from 0 to infinite. Minus of integration of differentiation of first, that is 1, into integration of second, e raised to power minus st upon minus s dt. Again limit are from 0 to infinite. Okay, so if you solve it out, so that will comes out to be fs is equal to 1 upon s square. Okay, so this is example of unit step, and this one is for ramp signal Laplace transform example. So let us discuss one more example. Suppose you have ft is equal to impulse signal, that is del t. Del t. Question is find out Laplace transform fs. Okay, so we will solve it out. fs 0 to infinite, here function is del t e raised to power minus st dt. So if you solve it out, you know del t value is 1 for t is equal to 0 and 0 otherwise. Okay, so if you solve it out, so that will comes out to be fs is equal to 1. Okay, we will discuss some more example in the next video lectures. So this is the basic introduction. We have seen here 3 basic example how to compute the Laplace transform. So before going in details, let us discuss what are the necessary conditions. We know the formula. Okay, so very simple. We know, we already discussed about the applications, why we need it, for the simplicity purpose or for solving out the differential equation or integral equation. So what are the basic requirement or necessity? So first necessity is basically integration by parts formula. Integration by parts formula. If you are interested in solving out the numericals of Laplace transform, then you must be aware about this integration by parts formula. Okay, so this is integration by parts. Sorry, this is integration by parts. This is integration. This is integration by parts formula. Okay, so what is integration by part formula? Suppose you have two functions, x1t and x2t. Okay, your two function x1t and x2t, and you are interested in finding out the integration of the multiplication of these two. So that will be given by, suppose that is some defined limit are there, x1t into x2t dt. So that will be given by the formula first function as it is, integration of second. Okay, minus integration of differentiation of first. Differentiation of first, that is differentiation of x1t in our current case, into integration of second, that is x2t dt, and overall integration of this. Okay, so this is the formula for the integration by parts formula. In our last case, this one was t and this one was e raised to power minus st. So apply this formula. First function as it is, integration of second function minus integration of differentiation of first function into integration of second function and overall integration dt. So this is integration by part formula. So you must be aware about the integration by part formula, or you can say you must be aware about the differentiation concept also, integration differentiation concept. So these are the basic necessity. Then only you will be able to solve out the Laplace transform. So this is the first necessary condition or requirement to be able to solve out for the Laplace transform numericals. So second one is the Euler equations. Okay, second one is the Euler equations. These are very important equations. So these equations are basically simply nothing. These equations are basically, suppose we have any exponential e raised to power j theta. Okay, so that must be written as e raised to power j theta. That must be written as just wait, e raised to power j theta. Okay, so that is written as cos theta plus j sin theta. Okay, j sin theta, cos theta plus j sin theta. So and similarly e raised to power minus j theta, e raised to power minus j theta, that will be written as cos theta minus j sin theta. Okay, minus j sin theta. So suppose this is equation number 1, this is equation number 2. So if you add first and second, first plus second, you will get first plus second, you will get cos theta is equal to e raised to power j theta plus e raised to power minus j theta upon 2. So remember this equation, this is very useful. Okay, we will utilize this equation in the coming numericals, next video lecture. Okay, similarly 1 minus second, if you 1 minus second, start equation number 1 minus equation number 2, then you will get the sin theta in term of exponential function, that is sin theta. So that is comes out to be e raised to power j theta minus e raised to power minus j theta upon 2j. So what is j here? Already know what is j here. What is j? J is minus 1 under root. Iota, we can say iota also. J square is minus 1, j cube is minus j, and j raised to power 4 is 1. Okay, we already know about this. So these are Euler equations which need to be considered, because in our case the one equation is always, in our Laplace transform formula, one equation is, one function is exponential function. So if the another function is suppose sine or cosine type function, then convert that into the combination of exponential function and then apply the integration by parts formula, and then our problem will be solved out easily. Okay, so this is the necessity condition. You must be aware of the Euler equations. So I have write down here the Euler equations. Just remember these. Then the very last part and very important one is that if you solve out something with the help of some transform techniques, so obviously our difficulty is reduced by some extent, but the question arises that the answer will also be in the transform domain. So transform means to convert one thing from original domain to some other domain. And why we are doing it? We are doing it basically so that our complexity get reduced. Already see in the previous slides that our complexity get reduced, our integration converted simply into multiplication. So I will here, before ending today's video lectures, I will discuss partial fraction expansion case, because these are very important for finding out the inverse Laplace transform. Okay. So partial fraction expansion, why they are necessary? To find out, basically to find out inverse Laplace transform. Inverse Laplace transform. Okay. Write down here. ILT is inverse Laplace transform. Inverse Laplace transform. Okay. Inverse Laplace transform. We will see about the linear Laplace transform in coming video lecture. So at present my motive is to make you aware about the partial fraction expansion. Basically there are three cases for the partial fraction expansion. Okay. First one is when the roots are simple. When the roots are simple root case. And here I am discussing about the poles. Roots are poles. That is roots of denominator polynomial. I will discuss it. So this is first case. Second case is when the root are multiple. When the root are multiple. Okay. And third case is when the root are complex. Conjugate. Complex conjugate. So I will discuss these three cases. So suppose, as we have already discussed, when we solve out any output with the help of Laplace, then we get this equation. Ys is equal to xs into hs. Okay. You already see it. Then here now this is transfer function. So hs will be written here like this. Ys upon xs. Okay. So this is basically numerator polynomial, this is denominator polynomial, or in technically you can say this is the Laplace transform of the output, this is the Laplace transform of the input or excitation, and this is Laplace transform of the impulse response. This is known as system function. Okay. This is known as system function. So roots of this are known as zeros and they are represented by small circle, and roots of denominator polynomial are known as poles. They are represented by small cross. Okay. Small poles, small circle for zeros and small cross for poles. So our case is partial fraction expansion. So first condition for the partial fraction expansion is that the function hs must be proper function. The function hs must be proper function. Must be proper function. Proper function. So what is proper function? The degree of the numerator must be lower than the degree of the denominator. If it is not so, simply do the normal division first, then apply the partial fraction expansion. So let us discuss the first case, simple root case, where by default root means poles. When the poles are simples. Okay. So case first. When the roots are simple root case. Okay. So suppose you have a function hs is equal to any function ns upon ds. Okay. Ns upon ds, or you can say suppose ns upon s plus a s plus b, suppose. So here you can say the poles are simple. The poles are at s is equal to minus a and minus b. Okay. At poles the function value become infinite, at 0 the function value become 0. Okay. So s is minus a and minus b. So in our case, if we solve out with the help of partial fraction expansion, then You can write down HS is equal to A upon S plus A plus B upon S plus B. Okay, so how to find out now? Motive is how to find out A and B. That's very simple. You already know in the mathematics also. I am just giving you refreshing, so that if you are not aware, then do the practice of this, because that is very necessary. So here A is S plus A multiply with the function HS and put S is equal to minus A here. So you will get A. Similarly B will be S plus B into HS into HS. Okay, and here S is equal to minus B. Okay, so this is the simple case. We will find out easily A and B here. So the second case is when the roots are complex conjugate. Second case complex conjugate. Okay, complex conjugate. Okay, when the roots are complex conjugates, then you can say HS is equal to suppose NS upon TS, that is NS upon suppose S plus AJ S minus AJ. So these are complex conjugate. Okay, so in this case just find out. So this will be equal to, you can say, A over S plus AJ plus B over S minus AJ. So here you need to find out only one, either find out A or either B, just like the simple case, and the second one is a complex conjugate. Okay, so suppose A here comes out to be, suppose A plus BJ. Okay, then in our case, so this is capital A, so let it be small, A plus BJ. Then B will be equal to A minus BJ. J is minus 1 under root. Okay, so this is complex conjugate case. If the roots are complex conjugates or the poles are complex conjugate, then just find out only one. The second one will be the complex conjugate of the first one. Okay, so let us discuss the third case. The third case is basically, little bit tricky. Multiple roots. Case. Okay, suppose take an example. HS is equal to NS upon S plus A S plus B square. Okay, so you will write down like this, A over S plus A. We are assuming here that this is proper function. Okay, this is proper function. We are by default assuming it, plus B over S plus B square. plus C over S plus B. So you can easily find out A and B, just like the simple case already discussed in the previous slide. But how to find out this one? So here we have to do differentiation. So how to find out this one? So here C will be find out. I am just discussing about the C. So C is basically D upon DS. That is basically 1 upon 1 factorial also. In this case, formula is 1 factorial into differentiation of D upon DS of S plus B square HS and here s is equal to minus b. Okay. Similarly, if the power is n, then that comes out to be c is equal to 1 over n minus 1 factorial dn minus 1 upon dsn minus 1 s plus b raised to power n hs, and here again s is equal to b. So this is the case of the multiple root case. So in today's video lecture, we basically discuss about introduction about the Laplace transform. Okay, why we need Laplace transform, what are the applications of Laplace transform. Okay, so that's all about for today's video lecture. Thank you students, and Jai Hind.